Okay, so we're going to start with a definition. And the first is that we're going to define a vector field to be called what we call a conservative vector field if there exists a function, and this is going to be a scalar function. We'll call it little f. And where this scalar function has the property that if you take the gradient of it, you get back to your original vector field. And we have a name for the scalar function. We call it the potential function. Okay, so examples of conservative fields, and you may be saying, well, I've heard this before in physics, so I can just tell you off the top of my head what I've been told are conservative versus non-conservative. Some examples are gravitational fields, and we're going to see for a minute, or we'll see after this, how you can tell in general which fields are conservative versus not, but these are just well-known ones, often from students from their previous experience in physics classes. Gravitational fields, electric fields are both conservative, and non-conservative fields are friction forces, so one example, and there are many magnetic fields that are non-conservative. So these are just some places you may have already heard this word before. But let's dig into the math behind what it really means to classify a vector field as this. So why does this matter? Let's notice what happens when we evaluate the work done by a conservative vector field. So just like we started at the warm-up, we know how to calculate the work done by a general vector field. In this case, we normally write it as f dot dr. But because we're saying it's a conservative field, I can replace f, this vector field here, with the gradient of little f, which is going to be some function. Okay, so these are equivalent notations. All right, let's actually expand this out and see how we would do this line integral. We're going to change variables just like we did on the warm-up, put everything in terms of t by parametrizing, and we're going to do this dot product between this gradient vector field and dr dt. Okay, so let's actually just expand out what this becomes. This is going to be the gradient. So recall back from chapter 11, when we take the gradient of a general scalar function, it's just this vector whose components are the partial derivatives. Okay, and then I'm going to dot that with dr dt, which is just going to be the derivative of my x parameterization, y parameterization, and z parameterization. Okay, so all we're doing is just following through how we already know to evaluate line integrals, but we're doing it for this special case where my vector field happens to also be the gradient of some function of x, y, and z. Okay, so let's actually just expand this out now. Okay, so now I want you to notice, all I've done is taken the dot product, expanded it out. This should look familiar. This should remind you of something from chapter 11. So what is this reminding you of? If you said, oh, you know, this is reminding me of the chain rule back from chapter 11, if I had a function of x, y, and z, and each of those were a function of t. And that's exactly right. What we can do is rewrite this, basically like think of the chain rule going backwards, and rewrite what I have here in my integrand as in fact just the derivative of my function f with respect to t. So that's this, and then dt. Okay, but now think of what we're doing. We are integrating the derivative of a function. We know from Calc 1 that this is going to simplify thanks to the fundamental theorem of calculus to just give us the function evaluated at t1 and minus the function evaluated at t0. Now, this is because I have a nested function, I'm going to write this a little bit carefully. This is a function of x, y, and t, and then due to the fundamental theorem of calculus, I can just evaluate it at the endpoint minus the starting point. And a nice shorthand way that we can write this is going to end up being, give me a second here. I'm going to call the starting point A and the ending point B. So I'm just going to say this becomes F at my ending point minus F at my starting point, capital A here. And so if you notice what just happened, this whole line integral only ends up depending on the value of the potential function where I end minus the value of the potential function where I start. It doesn't depend at all on the path, thanks to fundamental theorem of calculus. And so we actually have a name for this now. We call this the fundamental theorem of line integrals, because it's a way of seeing how the fundamental theorem of calculus plays out in line integrals. So let's summarize what we just proved. Just anytime you take the line integral of a conservative vector field, which in this case we can just write like this, it's only going to depend on your starting points and your ending points. And in fact, it'll just be the difference between the two. End minus F at the start. And what I mean by start and end is you have some path here, just draw it. And when I'm starting, let's say this is, we'll do it in t as well as x, y, and z. This is t is t0, this is t is t sub 1, and we'll call the point where you start here x naught, y naught, z naught, and we'll call this point here x1, y1, z1. Okay. We just realized that the work done is going to be path independent if you have a conservative vector field. And so let's summarize this. Actually, let's try to use this first.